I hope you are doing well. I'm really glad and I'm really excited for newcomers and new subscribers. I would like to welcome to all newcomers and I hope I can meet your need and your expectation. This is a channel that we share information related to signal processing and communications, and I make different playlists in signals and systems estimation theory, stochastic process, and I try develop the videos, and hopefully I can share some information that you really need. And you know, today I'm gonna talk about Bayesian philosophy and MMSE, and this is really important topic that we should consider. First of all, what is the difference between classic approach and Bayesian approach? In Bayesian approach, we consider the parameter as a random variable. It means we have some prior knowledge and we want to enter this prior knowledge to the estimation problem. How can we do this? We can consider a prior probability for our parameter. We consider our parameter comes from a distribution. How I can select the prior PDF? Based on the physics, based on the knowledge that I have about the parameter. And another thing that I can consider is the complexity and the mathematics of our estimator. Because in Bayesian approach, sometimes we have some p-dimensional integrations, and sometimes even we cannot have a closed form estimator, and actually it's so hard and it's tough in terms of complexity and computational load. So when we want to select a prior PDF, we should consider this. And of course, in terms of performance, it's obviously Bayesian approach has a better performance because you enter more information, you enter extra information to estimation problem, and this make your estimator better than the classic. Okay, let's start from MMSE and let's get started. We have a parameter I consider in scalar case. We have theta, it's unknown parameter, and the estimator is theta hat. And I'm gonna find theta hat. In classic approach, theta is not random, and we don't have any assumption about theta. But in Bayesian approach, theta is a random variable and it has a prior probability. Prior probability. And let's start doing estimation. I define estimation error, theta minus theta hat. I need theta and theta hat close in perfect manner. They should be equal. Okay, what is the criterion for minimizing the error? its mean square error. Expected value of theta minus theta hat power of 2, power of the error. Actually, this is the power of error, and I want to minimize power of the error. Let's clarify this expectation. Theta here is random, and theta hat is the function of observation. So there are two things that are random here, theta and x. Theta hat is a function of observation. X is our observation, and we estimate parameter based on the observation. Then I need joint probability density function of x and theta. This is joint PDF, joint probability density function. In classic approach, we have x semicolon theta. What is the difference? Here, this is the probability density function of observation. Theta is a parameter of PDF. It's not a random variable. But here in Bayesian, theta is a random variable, and this is a joint probability of observation and parameter. Okay, how can I compute this expectation? We should integrate theta minus theta hat power of 2 p x and theta d theta d x. X can be a vector, and when it's a vector, I mean the x is n-dimensional differential, and we have an n-dimensional integral. But I just put one integral here for x. Okay, let's minimize this with respect to theta hat. You know that we can write probability density function like this. P theta given x multiplied by probability of x. This is based on Bayes' theorem. And we can see another probability. In Bayesian philosophy and Bayesian literature, we call this posterior PDF. Posterior PDF. There are two terms here, prior probability, posterior probability. Prior PDF and posterior PDF. The probability and the PDF after observing the data. P theta given x. I put px and theta based on this relation. Let's continue. P of x is positive, is a probability density function, then it must be positive. And I'm gonna minimize this with respect to theta hat. So what only I need to minimize this term. And for minimizing this, I take derivative with respect to theta hat. The variable of integral is theta, and the term and the variable for derivation is theta hat. So I can insert this derivation to inside the integral and put it on this term. We have minus 2 theta minus theta hat, here theta given x, here theta. This must be 0, and we have theta, here theta given x, here theta. Theta hat is the function of x, so I can write it here. And you know the area under the probability density function is 1. And finally we have theta hat, the MMSE estimator. Theta, here theta given x, here theta. This is expected value of theta given x. It's a conditional mean. Actually, this is the mean of posterior PDF. So if we want to recap our discussion based on MMSE estimator, if I want to estimate theta based on the observation and our criterion is MMSE, we just have to compute mean of the posterior PDF. In future videos, I will bring some examples of MMSE estimator. Thank you for watching this video.